Welcome to this introductory lecture on set theory. Let me start by motivating the study of sets. This course, called Mathematics for Computer Scientists, is essentially the study of discrete structures that computer scientists use all the time. Important discrete structures include relations, functions, and most importantly, sets. In fact, set is probably the most foundational discrete structure relevant to us. So let me give you examples of discrete structures that computer scientists use regularly that are based on sets. First of all, a function is a special kind of relation, and a relation is a special kind of set. So functions are sets. And by the way, a function has a set as a domain and a set as a range. Now, graphs, which you study a lot in computer science, are also sets, namely sets of vertices and sets of edges. Another example, and I'll stop there, is finite state machines, which are also defined using sets. So sets are really important, and in this first segment, we're going to define some basic terminology having to do with set theory. So let's start by defining a set. A set is an unordered collection of objects. That's a pretty general definition. Let's look at a specific example. Let's consider the set called S, and we typically list the elements of a set between curly braces. Here the first element is the number 2. The second element of the set S is that box, that square. The next element is the number 1. And the last element is a string set. So the first thing to notice is that the elements of the set, what you can put in a set, are objects, meaning pretty much anything. Numbers, actual objects, strings, and even other sets. The second thing to notice is the order of the elements in the set does not matter. The collection is unordered. So 2 is not really the first element in the set, and the square is not really the second element. That's just the order in which I happen to have listed them. So a set is very different from an array in computer science. First of all, an array typically contains only elements of the same type, which is not the case for a set, as this example illustrates. You can mix and match integers and strings and any kind of objects. So one way to think of a set is maybe as a backpack in which you can throw anything you want. Notebooks, pencils, pens, ring binders, and the order of the elements inside the backpack do not matter. So that's a very general definition for what a set is. So now let's consider some other sets, some other examples that are well known and that have well defined definitions and names. The first one is the set of non-negative integers or natural numbers, denoted by the letter n here, the thick letter n. Notice the ... here indicate that I am not done listing the elements of the set. In fact, this set is infinite, so the list goes on forever. But it starts at 0 and it goes up from there. Another well-known set is the set of the integers, including the negative integers. Again, the order doesn't matter as long as you get all of them. Here the pattern is to start with 0 and then go up by 1 and right away listing the negative element corresponding to the positive one. Again, this is another set that is not finite. Hence the ... Third well-known set is the set of rational numbers. Now here it's interesting, the way we define the set is not by listing its elements. It's by using a special notation called the set builder notation. So here is how you read this notation. It reads like Q is the set of the fractions of the two objects P and Q such that P and Q are integers and Q is different from 0. So the set builder notation is a concise way of defining the elements of a set by first stating the kind of elements that we're considering, in this case, fractions of two kinds of objects, and second, after the vertical bar here, which is read as such that, is listed one or more conditions that all the elements in the set must satisfy. Another well-known set is the set of all the real numbers, whose contents I'm not going to try to describe here, but I assume you're familiar with them. A very special set is called the empty set. That's the set with 0 or nothing, no element in it. It's usually written as a pair of empty curly braces here, or more commonly with this special symbol, which is different from 0. Again, this defines a set, namely the empty set. Another type of set is called the Singleton set. These are all the sets that only contain one element. For example, the set containing the integer 10, that's a singleton. Another example is the set containing the empty set. This is the first example of a set inside of another set. And the last example of a singleton is a set containing the single set, namely this one. So these three sets are singletons, by definition, since they each contain a single element. By the way, I've been using that term for a while, so let's write it down. We call the element or a member of a set one of the objects that are contained in the set. For example, the number 10 here is an element of the singleton set containing only 10. And this is the symbol we use to represent set membership. So on the right-hand side must be a set, and on the left-hand side must be an element or member of the set on the right. And here is the symbol for the negation of set membership. This proposition states that the number 10 is not an element or a member of this set. Remember, this set only has one element, and that's the singleton set 10. The number 10 is not the same as the set containing 10. Here's a third example of set membership that states that the empty set is a member of this two-element set. And this is the first example where we have a set on the left-hand side of the membership symbol. It's possible to have a set there because sets can contain other sets. Remember, on the right-hand side, you must always have a set for this symbol. Now let's define set equality. We say that sets S1 and S2 are equal, denoted by this, when the two sets have exactly the same object in them. A more formal way to write this down is to say that for all x, if x is an element of S1, then it must be also an element of S2 and vice versa. We have an equivalence here, if and only if. So that's the logical way of writing the definition of set equality. So for example, the set 2, 1, 2, 1 is equal to the set 1, 2, since the order of the objects in the set do not matter. These are the same sets. The next definition states that S1 is a proper subset of S2. Intuitively, that means S1 is contained in S2. In other words, every element of S1 is also an element of S2, but S1 is not equal to S2. That means there must be at least one extra element in S2 that is not in S1. So the formal definition states that for all x, if x is a member of S1, then x must be a member of S2, but not necessarily the other way around. In fact, another condition is that the two sets S1 and S2 are not equal. That's why it's called, S1 is called a proper subset. Proper means it's a subset that's not equal to S2. So for example, the set of natural numbers is a subset, a proper subset of the set of integers, since every natural number is also a member of Z, but there are extra elements in Z, or the negative numbers, that are not in N. So that fits the definition of a proper subset. Here's another example. Not much need for comment here. And the negation of being a proper subset is denoted by this symbol. Notice 1 is not a proper subset of 1, 2. First of all, 1 is not a set. So notice for this symbol, both the left-hand side and the right-hand side must be sets. 1 here is an element of this set, but it's not a subset. And here is a second counterexample of the proper subset relationship. So notice here that both the left-hand side and the right-hand side are sets. But to check if the left-hand side is a proper subset of the second one, we need to go through each and every element in the first set and check that it's also in the second set. So 1 is an element of the first set. It's also an element of the second set. So far so good. 3 is an element of the first set, but it's not an element of the second set. Notice this is the set containing 3. That's not the number 3. Because this element is in S1 but not in S2, then S1 is not a proper subset of S2. A similar concept is the concept of subset. Notice a subset is basically the same as a proper subset, but you add the equal sign here, which means S1 is a subset of S2 if S1 is a proper subset of S2 or it's equal to S2. So the formal definition is almost the same as for a proper subset, but there's no requirement that S1 be different from S2. So for example, the set 1, 3 is a subset of 1, 2, 3. Now let me ask you this question. These two properties, these two definitions are very similar. One is stronger than the other. That means one implies the other. Which way does it go? Does being a subset implies being a proper subset, or is it the opposite? A proper subset implies being a subset. Let you think about this for a while. Well, clearly, this is the stronger relationship of the two. Notice it has an extra condition here. So yes, being a proper subset implies being a subset. For example, this set here is a proper subset of this one, which implies, as we stated here, that it's also a subset. But the other way around doesn't work. For example, the set Z is a subset of itself, but it's not a proper subset of itself. So that's the distinction between the two. So let me ask you a true-false question now. Is it true that for every set S, the empty set is a subset of S? And the answer is yes. Go through the definition. The definition is right here. This is a conditional. Notice if S1 is the empty set, then X belongs to S1 is always false. There is no element in S1. If the hypothesis is false, then the the conditional is always true. Therefore, the empty set satisfies this definition. Therefore, the empty set is a subset of every set. Here's another true-false question for you to think about. Is it the case that for every set, S is a subset of itself? The answer is yes. I'll let you check that against the definition. Now, since this segment is getting a bit long, I'm going to stop it here, and in the second segment, we will continue with some basic terminology of set theory.